In this module, I am going to discuss about spectroscopy technique in the form of MCQ. Question number 1. In NMR spectroscopy, sample nuclei absorb electromagnetic radiation in dash region. Option A, radio frequency. Option B, IR radiation. Option C, X-rays. Option D, microwave. The resonance frequency for protons fall within the radio wave range, anywhere from 100 MHz to 800 MHz, depending on the strength of the magnet. Hence, the correct answer, option A, radio frequency. Question number 2. ASR spectroscopy uses dash radiation. Option A, visible radiation. Option B, microwave radiation. Option C, radio wave. Option D, UV radiation. Electron spin resonance spectroscopy is an absorption spectroscopy technique. It uses microwave radiation to create transitions between the magnetic energy levels of unpaired spin electrons. Hence, option B, microwave radiation, only the correct answer. Question number 3. Which of the spectroscopy techniques require electromagnetic radiation with the highest frequency? Option A, IR spectroscopy. Option B, UV spectroscopy. Option C, ESR spectroscopy. Option D, NMR spectroscopy. High energy electrons are used in UV spectroscopy because ultraviolet light corresponds to higher energy levels compared to visible or infrared light. When UV light interacts with a molecule, it can promote an electron from a lower energy orbital to a higher energy orbital, creating an excited state. The energy of UV light is sufficient to excite electrons to higher energy levels, which is essential for probing the electronic structure of molecule. The correct answer for the question, option B, UV spectroscopy. Question number 4. The rotational spectroscopy cannot be applied to detect option A, moment of inertia. Option B, interstellar space. Option C, electronic transition. Option D, bond length. The correct answer, option C, electronic transition. Question number 5. An absorbance shift towards a longer wavelength caused by chromophore is called dash. Option A, hypochromic shift. Option B, hypsochromic shift. Option C, hyperchromic shift. Option D, bathochromic shift. The correct answer, option D, bathochromic shift. Bathochromic shift can occur when the molecule is placed in a different solvent with varying polarity or refractive index. The extension of conjugated pi-electron systems can cause the shift in the absorption of light towards the light of the longer wavelength. Changes in the molecular structure, such as the addition of functional group, can lead to bathochromic shift. Changes in pH can alter the protonation state of a molecule. In turn, it can affect its electronic properties and lead to a bathochromic shift. Molecules can interact with each other through non-covalent interactions like hydrogen bonding or van der Waals forces. These interactions can affect the electronic structure and cause a bathochromic shift. Temperature changes can influence the electronic transitions in a molecule, leading to shift in the absorption or emission spectrum. Larger molecules often exhibit bathochromic shift. Bathochromic shift can occur when there is a change in its distribution of electron density within the molecule. For instance, the addition of electron donating group can shift the absorption or emission to longer wavelength. Bathochromic shifts are essential in various fields as they provide valuable information about the electronic structure and properties of the molecules.